Hi, this is Professor Fernandez. In this video, we're going to work through example 4.15 from Calculus 2 Simplified. So this one says, use the direct comparison test to investigate the convergence of each series. Down here, I have pasted in the direct comparison test. This is theorem 4.11 in the book. So I just want to go through it really quickly so we get a sense of what we're going to need to do to use this test. The theorem says, suppose I have two series, then if B sub n converges and B sub n is larger than the A sub n, then A sub n converges. In other words, translation, if I want to show that a series converges and I can find a larger series that also converges, then the direct comparison test tells me, yep, that original series converges. Also, it goes the other way in terms of divergence. Suppose I want to show that a series diverges, and I can find a smaller series, right? Bn is less than or equal to an, smaller series that diverges. Then the direct comparison test tells me this diverges. Okay, so depending on what you are thinking about the series an, you're thinking it converges, you're thinking it diverges. The direct comparison test can help you conclude that, provided you satisfy all of these hypotheses, right? So let's go to the example and let me show you then how you can use the direct comparison test in 4 different ways, right? So that's the idea of these 4 examples, to show a series converges or diverges. Okay, so in the first example, what we're going to do is we're going to use information about the values of cosine of n, basically. So as with all the series, right, you want to get a certain sense of whether it converges or diverges right from the series itself. We know that cosine squared n is only ever at its largest 1 because cosine of x, remember the graph of that, kind of just oscillates between -1 and 1, right? So the largest it ever gets is 1, the smallest it ever gets is -1. If I square that, then I'm making all these negative values positive, so the graph of cosine squared looks a little bit kind of like that, right? Still, the largest value is 1, the smallest value is 0. So that explains why cosine squared n is less than or equal to 1. It's also bigger than or equal to 0. Sometimes it's 0. But importantly for us, right, the times that cosine of x equals 0, right? Remember when that happens. For example, over here, that's when x is pi over 2, right? And then over here, that's when x is minus pi over 2. So these are all irrational numbers, right? They don't have terminating decimals that have some repeating pattern in them. They're definitely not natural numbers, which is what the n's in series always are. Why is all this important? It's important because we now know that cosine of n squared not only can never be equal to 0, because again the n's are 1, 2, 3, 4. Also, we know that it's at most equal to 1, right? We don't have to worry whether or not it actually is equal to 1. We do know that it's at most equal to 1. So if I take this inequality and I divide everything by n squared, right? Noting again that n squared is never 0, it's never negative, so that would not flip the inequality signs for me. Then what do I get? Well, on the left-hand side, I get 0 again. In the middle, I get the terms that are in my series up here. And on the right-hand side, I get this. Okay, so now if we remove all this clutter and we kind of talk about what we have achieved, we've now just seen that the terms in this series, right here, are less than or equal to 1 over n squared. They can never be more than 1 over n squared. So now if I look at adding up all these terms, right, then the thing in the middle is the series I'm looking at. The thing on the left-hand side is 0. So the thing in the middle is the series I'm looking at. And on the right-hand side, I have the sum from n equals 1 to infinity of 1 over n squared. Hey, that's something you might recognize. That is an example of a p-series, where p equals 2. Remember, p-series have the form 1 over n to the p. And in this case, p equals 2. And because 2 is bigger than 1, then we know that this p-series converges from our p-series theorem. So this series converges. So if we step back, what do we got? We got a series we're trying to determine convergence or divergence for. we have found a larger series that converges. So there we go. If we're thinking that we have found a larger series that converges, then the series we're looking for, the direct comparison test tells us, converges. Okay, so series up here converges. Great. We don't know what it converges to, right? That would be a question of find the sum. We're not asked to do that. So we're going to move on to the second example here. Example B. So here I have a different series. Again, it's useful to get some intuition for what's going on here. I can't bound the numbers here so easily, right? 2 to the n is kind of like an exponentially growing function, so it doesn't oscillate between two numbers like cosine did. But here's what I can do. I can say, hey, 2 to the n plus 1 reminds me kind of 2 to the n. So especially when n gets really big, right, 2 to the n is going to be really, really large compared to 1. So this entire series is going to look increasingly more like 1 over 2 to the n. This is 1/2 to the n, and that's going to then be a geometric series with r equals 1/2. And because the absolute value of r in this case is less than 1, it'll be a convergent geometric series. So what I'm sensing here is that this series is not a geometric series, but eventually it becomes very, very indistinguishable from a geometric series that converges. So I think that this series is going to converge. Moreover, I'm going to try to use this geometric series to establish that result using the direct comparison test. Okay, so like I said before, with the direct comparison test, if you think the series converges, you want to find a series that's bigger than the series you think converges. Here's how to do that for part B in this example. So 2 to the n plus 1, right? We just kind of compared that to 2 to the n. We did that by dropping the plus 1, thinking about what if n gets larger, what happens? 2 to the n plus 1 looks like 2 to the n. But we need inequalities for the direct comparison test. So here's how you come up with those inequalities. You ask yourself, what is the relationship between 2 to the n plus 1 and 2 to the n? Well, this is literally 1 more than that, right? So it's larger, bigger. And that gives me all the information I need. There's the inequality that I'm going to use. How do I go forward from there? Well, I take the reciprocal of both sides. Once I do that, then the inequality sign flips, right? So that gives me a new inequality. And lo and behold, this term really is larger than that one. And so if I look at the sum that I'm interested in, which is this one, n equals 0 to infinity, that's going to be less than this sum, n equals 0 to infinity, 1 over 2 to the n. And again, we talked about earlier how this is a geometric series with r equals 1/2 that converges. So I've set up all the information that I need for my direct comparison test. I found a convergent series that is larger than the one I'm looking at. So here's the series that I'm looking at up here on the upper left converges by the direct comparison test. So yes, we'll eliminate the question mark, and indeed we verified convergence. Okay, so notice the different approach that we took in part B, right? We dropped a number. Equivalently, we asked ourselves, if n gets really, really large, what does this denominator start looking like? It starts looking like 2 to the n. And then 1 over 2 to the n we recognize as a geometric series. Let's use the same exact approach in part C, but we'll see that this series probably will diverge. How do we know that before doing any of this inequality stuff? If you take a look at this series, it kind of looks like 1 over n, right? The series 1 over n, which is the harmonic series. And we know that this series diverges. Okay, how do we know that it kind of looks like it? Well, the 3 just would maybe, stay there and maybe look like 1 over 3 to the n. It's like, 1/3 of the harmonic series. The minus 2, similar deal. So if we look at 3 to the n minus 2, as n gets large, so large n values, the minus 2 becomes more and more inconsequential, right? Think of n being like a trillion. So 3 trillion minus 2 is really, really close to 3 trillion. So for that reason, using the same kind of argument from before, we're like, hey, basically we just drop the -2. I need an inequality. So now I have to relate these two terms together. And I say, oh, wait a minute. When I subtract 2, I get something smaller than what I started with. And so now we take reciprocals just like before. So that flips the inequality sign. And here I am. And now I'm just going to, swap the direction, the order of these, so we can kind of see things a little better. Okay, so now on the left-hand side, I have something that's smaller than the thing involved in our series up here, right? So if I look at the sums, right, this sum is basically a harmonic series, right? It's 1/3 of a harmonic series. So that diverges. And we have shown that the terms of this basically harmonic series are smaller than the series that we are looking at. And so back to the comparison test, if I found a divergent series whose terms are smaller than the series we're looking at, then the direct comparison test tells me that series I'm looking at diverges. So we're going to go back up here and say, aha, this series diverges. Diverges. Okay, so the first two examples that the last two examples, this one and the previous one that we just did, involved dropping numbers, right? So we dropped the +1, got 1/2 to the n, geometric, did that. Here we dropped the -2, got 1/3 to the n, sort of harmonic, so we use that. This last example, part D, is going to introduce us to yet another way that you could approach these questions for direct comparison tests. Remember, the objective is always to find that precious inequality of the terms that's required by the test. Okay, so you could try the approach here of dropping the 7, right, along with B and C. But I want to introduce you to this other approach, which says, hey, one of the reasons why you might think to drop the 7 is that this is a much easier series to analyze. This is 5/4 to the n. That's geometric, r equals 5/4, and that diverges. Great. But, you need an inequality sign. And, comparing 4 to the n plus 7 to 4 to the n, well, this is larger. And if you then took reciprocals and you did this, and you multiply by 5 to the n, this isn't really going to help you, because if we want to show this series converges, remember we have to find a smaller series over here that we know converges. Over here we have found a larger series, right? So this is not going to work so easily as just dropping the 7. So let's talk about how it would work. So what could we do? We could say, well, I still want to relate 4 to the n plus 7 to 4 to the n. And here's one of the ways you can do this. You can say, well, what's the relationship between 4 to the n plus 7 and 2 times 4 to the n? And you can kind of investigate this for yourself, right? What if n equals 1? 4 to the first plus 7 and 2 times 4 to the first. This is 8. This is 11. So again, I'm looking for the relationship here. Well, this would be larger. Okay, how about if I go and do n equals 2? I compare these two. Well, now I have here 16 times 2, 32, and over here I have 16 plus 7, 23. Aha, so this one is bigger. And this should kind of make sense, because here I have on the right-hand side 2 times 4 to the n. This is 4 to the n plus 4 to the n. And over here I only have 1 4 to the n and then a 7. So here I have 2 exponential functions growing, at the same rate. Here I have 1 exponential function and then just plus 7. So eventually this right-hand side is going to win out. It's going to have larger y values. And what we've just shown is that that starts to happen exactly when n equals 2. So 2 times 4 to the n starts being larger than 4 to the n plus 7 when n, so 4n equals 2 or larger. By the way, this is exactly where the series starts. So this is one way we know we're on the right track. We have understood one of the clues as to why the series does not start with n equals 1. Even if it did, we could use the approach we're using now. We would just have to look at, separate out the first term, start the series at 2. Okay, so we have our inequality, great. And now I'm going to take reciprocals, right? So if I take the reciprocal here, that flips the inequality sign to this, 1 over 2 to the 4, 2 times 4 to the n. Now I'm going to go back and look at the terms in my series. I'm missing the 5 to the n, and I'm going to remember that 5 to the n, because n is 2 or larger, is always positive. And actually 5 to the n is an exponential function, always positive anyway, but again, using the information we have. So now I'm going to multiply the entire inequality by 5 to the n. On the left-hand side, I get this. On the right-hand side, I get this. And now things are starting to look pretty good. Again, I'm going to swap the order here so that we realize that the series that we want information about, we have now found a smaller series. Here it is. And this one is 1/2 times the series 5/4 to the n. Okay, so now we're getting somewhere. So this is a geometric series with r equals 5/4. Because absolute value of r is larger than 1 in this case, right? All we need is that it has to be larger than or equal to 1. Then the geometric series we have here diverges. So we have found a smaller series to the one we're studying, smaller series that diverges. So we go back to the direct comparison test. We found a smaller series to the one we're studying, and that smaller series we saw diverges. So direct comparison test tells us the series we're studying also diverges. So we go back up here, we eliminate all the clutter, and we conclude here diverges. Okay, to recap what we've done, and as a way of just telegraphing once again the different ways that you could use the direct comparison test. In part A, the first thing that we did, and this is one thing you can do when using the direct comparison test, is to look for bounds for functions in the series. Right? If you rewind, right, we basically talked about this. The fact that the values for cosine as a function oscillates right between -1 and 1. So that was a bound that we got straight from looking at some of the functions, in this case the numerator, involved in the series. So that really helped us for part A. For part B and C, what we did is we dropped numbers. Right? So over here, remember, we said, oh, 1 over 2 to the n plus 1. This part kind of looks like 2 to the n, right? So this thing is geometric, convergent, and then that helped us out. Over here, we're like, oh, 3n minus 2. This kind of looks like 3n. And then this is harmonic, divergent. That helped us out. Okay, in part D, we used a very different tactic, right? So like we said earlier, if you rewind the video, this drop the 7 didn't exactly work out. But there, we used a different approach. So replace one of the terms in the, and I'll say maybe expression, one of the expressions, so not confuse term of the series, one of the expressions in the series with another one in the series. Okay, so what I mean by that is if you look at what we ended up doing, right, we ended up taking this series, right, these terms, and then comparing it to this series. All right. In other words, we replaced the 7 with something else in the series. We replaced the 7 with 4 to the n. And if you go back a minute or two, you saw how that actually helped us conclude that the series diverges. Okay, so these 3 approaches are pretty much the standard approaches to using the direct comparison test in terms of how you would find the inequalities that you'll need for the test. And these 3 approaches work beyond these 4 examples that we've seen, right? I would even go off on a limb and say that pretty much every question that uses the direct comparison test you might be asked in your calculus class will require using one of these 3 approaches. And now you've seen examples of how to do that. Great, see you next time.